All right, everybody, 4 o'clock. Welcome in. Back to your favorite class. Yes. Right. You know, I keep saying it, it'll be true. I keep forgetting to change. It's not the lab class. This is a normal lecture. What am I doing? Okay, announcements. I did post a new homework for you guys on sort of this micromechanical strength theory as well as some of the transformation stuff for thin laminates that we talked about last time. So take a look at that and do that. That'll be due next Thursday. Also, a reminder, next Tuesday, you have your manufacturing depth document that is also due. All right. So appreciate the meme spamming in the, in the chat right now. That's pretty. I like that one, Justin. That one's pretty good. That one. The SpongeBob at the 100 degrees. Fahrenheit, he chilling. Even though I think Fahrenheit, he's probably like not very happy at 100 degrees. Preston wants to know if you get extra credit for a meme in your homework. It won't hurt your chances. Just like Harvey Dent says in the Batman movie. Can't hurt your chances. All right. Okay. So homework 6 and your manufacturing depth document. All right. Make them sparkle. Dang it. Very nice. With the Borat meme. Very nice. Okay. Let's pick up where we left off. We're probably going to finish up with the micromechanical strength notes today. Just as a reminder, our micromechanical strength notes, I want to go back and give kind of a higher level view of where we are. Remember, we had theories for kind of like the 5 types of loading that are probably the most common in the general principle directions. That would be longitudinal tension. All right, and we kind of did this one, so maybe I'll give this guy a little check mark. This is the one where we have, you know, a more brittle matrix or a more brittle fiber. What happens? Low volume fraction, high volume fraction, sort of all that nonsense that was associated with that. This is kind of like the most difficult. At least in my opinion, it's kind of the most complicated. The second we did was transverse tension. And this one we also did, kind of dominated by stress concentration. This is a reminder what we call these. This is F1T. This is F2T. Failure in the 2-direction of tension. And we had just finished up last time with longitudinal compression. All right. So we had kind of just finished up with that guy. This is F1C. Failure in the 1 direction in compression. And we got 2 more to do, which we'll get through today, which is transverse compression. Which is F2C, obviously. And this will be today. And the last one is sort of macro level shear. All right, and this is going to be F6. Right. And that's because it's this in-plane 6 direction, which is like the 1-2 direction, which we for some reason call the 6 direction. Okay, I do want to just run this back really quick with the longitudinal compression and kind of talk about or summarize what we did last time, and that's where we'll pick up. All right, so longitudinal compression. A summary. Once upon a time, there was a unidirectional composite. He was put into compression, and then he failed. The end. Okay, that was my summary. No, just kidding. This longitudinal compression also kind of complicated, right? You remember it kind of looked like this. Fibers in here this way. Our longitudinal compression is kind of compressing in the one direction this way. Some stress in the one direction. I keep forgetting to play the One Direction soundtrack in the waiting room. Okay. We said that there was kind of three ways that this could fail. Buckling of the fibers could fail in transverse tension while in compression, a little strange, and it also could fail in shear. So 3 modes failure. Kind of the first that we talked about was this buckling mode. Which led to that like kink banding. Hopefully we sort of remember the pictures of that. My favorite rock group, kink band. All right. Happen in 2 different ways, either in phase or out of phase buckling. So I'll say let's call it 1A. 1A, if you're from Canada, it's 1A. So we had out of phase buckling. And this generally was for low volume fraction. And in that case, the fibers were far enough away from each other where their like buckling behavior was not influenced kind of like by the neighbor next to it. Maybe that guy's got a lot of buckling modes, something like that. All right, they're far enough where they're not really like communicating their buckling. All right. And in this situation, we saw that the failure strength was the following: 2 times VF quantity modulus of the matrix times modulus of the fiber in the one direction times volume fraction of the fiber, all divided by 3 times 1 minus volume fraction of the fiber. This is all to the 1/2 power. This is for volume fractions like 15% or less-ish. And I'll say ish. This is my air quotes, 15%-ish. All right, we also said that there was like this in-phase buckling, 1B or not 1B. So this is higher VF. In the picture here, there's enough sort of density of fibers inside the material so that when you load it, they're all kind of like buckling in the same way and buckling like in phase with each other, fifth element style. Boy, that's a complicated one. Which stone was that? I think that was the air stone from Fifth Element. Yeah. No one has any idea what I'm talking about, but that's okay. In this situation, we're kind of governed by properties of the matrix because the matrix is going to kind of fail in shear near where those kink bands are going to form. So here we have F1C equal to the modulus of the matrix, which is sort of a weird phenomena, 1 minus VF. And so this is for volume fractions like 15 to, I don't know, 60 or 65%. Let's say 65%. And again, this is ish. Okay, close. All right, the second way that we saw that we could fail in longitudinal compression was in transverse tension. Complicated. And this is Poisson effect. All right, so if we're kind of looking down the one direction, That's what you kind of want to think of in your head here. Here's your 2-3 plane. Looking down the one direction, you got all these fibers like in the plane here, and you're compressing into and out of the plane. And by compressing into and out of the plane, you're going to create strains, tensile strains in like the 2 and 3 direction. And that's coming from sort of this compressive stress into and out of the plane. And you could have a situation where you're compressing in the one direction, and that's causing so much tensile strain in the 2 and 3 directions that this is actually failing kind of at this interface between the fibers and the matrix, because this is just such a weak, directional strength for these composites because of the stress concentrations of the fibers. Okay. So we kind of derived this, or looked at kind of what this would be. This has kind of a couple forms. But here, this is, I gotta go back to my notes here, make sure I get this right. F1C here is going to be the modulus of the composite multiplied by the strain that would cause failure in tension in the 2 direction divided by Poisson's ratio of the composite. So something that we derived, which if you sort of use your rule of mixtures to sort of expand some of these things, you'll have EM VM plus EF1 VF1 multiplied by the strain that would cause failure in tension. So here that's just going to be the stress that would cause failure in tension, F2T, divided by the modulus of the composite in the 2 direction. All this divided by Poisson's ratio 1:2, which is going to be Poisson's ratio 1:2 of the fiber times volume fraction of the fiber plus Poisson's ratio of the matrix, volume fraction of the matrix. Complicated. All right, so that was kind of like failure mode number 2 for longitudinal compression, which is transverse tension. And then the third failure mode was one that's very rarely seen, is sort of this like just macro level shear failure. Okay, kind of the picture you want to have in your head for this type of failure is a composite that sort of like fails at a 45-degree angle. From the load that you're putting on. There's kind of a nice picture of this in the notes. I'll do my best to sort of replicate here, but I'm not the best artist. The zebra composite. In reality, the volume fraction would be much higher than this, but I'm just exaggerating the picture so you can kind of get an idea for what's happening. And we've, put so much stress on this, and the fibers are not able to buckle because there's just so many of them next to each other. They don't have the ability to wiggle, that ultimately the fibers just fail in shear, all together with this sort of like shear mode here. Okay, sort of like slipping against each other. This here is going to be governed by the actual shear properties of the fibers themselves, because you're actually like shearing mostly through the fibers because you have so much volume of fibers in this particular material. So this is very high volume fractions. So this is like 65% or more ish. And again, these are all kind of just approximate values. It really depends on the material properties. But here, this is going to be governed by properties of the fiber in shear multiplied by some constant. So here we have F1C going to be equal to 2 times the failure of the fiber in shear, that's FFS, times volume fraction plus 1 minus volume fraction multiplied by the ratio of shear properties of the matrix to shear property of the fiber 1, 2. Okay, dang, longitudinal compression, also complicated. For different reasons than longitudinal tension is complicated. Dang. All right, looks like I still have a notification here. Oh, someone got my Fifth Element movie reference, so I'm glad for that. Lucas, did you have a question? Will in-phase and out-of-phase equations produce a similar answer if you use them both VF equals 15%? It really depends on the material, Lucas. So you'd have to know things like the modulus of the matrix, the modulus of the fiber to really answer that question, because you'll see in like the equation for out of phase buckling, those material properties kind of manifest. So really depends on the properties of the material. That's why I say 15%-ish is like this boundary, okay? Really depends on the properties of the materials. David asks, when are 15% VF composites used? When you have bad manufacturing technique, that's when. No, actually a lot of like natural fiber composites can sometimes be hard to manufacture at high volume fractions. Just because natural materials, if you're trying to use them, sometimes they don't, cooperate as well. So sometimes that's the case. Or if you have bad manufacturing practice. All right, so that's your longitudinal compression. Onward. Now let's compression. Fortunately, it is quite similar to transverse tension, and that it's dominated by stress concentrations. Someone find me the Fifth Element air stone, and I'll show you what I mean by my picture. Doesn't really make a lot of sense, but if you can find the picture of it, it will make more sense. All right, so transverse compression, picture you're going to have in your head is here. So here's all your fibers inside of your material. Your 1, 2, 3. And we're putting the 2 and 3 direction in compression. Okay. So here's like sigma 2, or equivalently, like you could, sorry, this is the 3 direction. Might be. I'll stick with kind of how I drew it. It's more or less equivalent. And if you're looking in the 2, 3 plane, you're going to see the following. Okay. Okay, so if you've got compression of these circular elements, you're again going to have failure that occurs kind of like at the boundaries of these fibers, generally inside the matrix. This is really the only failure mode that we have. So again, this is going to be sort of heavily dominated again by transverse tensile, or sorry, by stress concentrations. Dominated by stress concentrations. And it's very similar to failure in transverse tension. Though generally it's not as bad. The tensile 2 direction is going to be worse than the compressive 2 direction. So here, the failure F2C is again just going to be dominated by stress concentration. Where this is the failure of the matrix material in compression, which usually is higher than that of the failure stress of the matrix in tension, divided by this K sigma value, this stress concentration value. And I'll remind you what K sigma is in just a second. Did somebody find me the fifth element? Yes, there it is. That's the water. Dang, get me the air one. That's close though. The air one goes up and down. But that's close. Anyone that's seen the movie. All right. Remember your stress concentration given by things like volume fraction. It's governed by volume fraction and properties of the matrix and the fiber. Here we're going to use 1 minus, this is the same one that we did in transverse tension. 1 minus EM. Here now EF2. Again, because we're in kind of this two direction. 1 minus, here the square root of 4VF on pi, multiplied by the quantity 1 minus EM on EF2. And this is your stress concentration factor. Did we find it, Kev? Yeah, Alex has got it. This is the air right here, the one with the lines up and down. There's your micro buckling right there. Can I get that? Can I blow that up? Make it bigger. There we go. High resolution image. There's your micro buckling right there. See how all those fibers are buckling together? Fifth element. You didn't think you were going to learn something today from the fifth element, did you? But there you go. What put Mila Jovovich on the map before Resident Evil, if you can believe that. All right, so that's transverse compression. Pretty simple. Again, dominated by stress concentration. The two directions easy, in my opinion. It's just easy to understand that you're going to be dominated by stress concentrations in those general directions. All right. I guess we can make one last note here before we move on. But usually F1C is greater than F2C is greater than F2T. The magnitudes here, if you want to be kind of appropriately mathematically, usually maybe about by a factor of 2. All right. So remember this two-direction tension, very weak, very, very weak. All right. Last kind of mode we need to talk about. One last thing, I'll show this nice picture from the notes about compression just because I think it's kind of a nice looking picture. This guy here, two direction in compression. You can see these guys are kind of failing at this interface between the fibers and the matrix because of the heavy stress concentration. Okay. That's from your books. Nice picture from your book. All right. Last mode of failure we'll talk about is in-plane shear failure. Okay, what this guy looks like. We're going to apply a sigma 6. So again, here's our composite. We got the fibers in it. And here we have like a pure shear on our sample. So we have a shear 1, 2. So it's going to be on the one face in the two direction or on the two face in the one direction. So more or less that's kind of like crawling up this face this way and crawling up this face this way. That's kind of your shear that's being applied. So this is sigma 6, or what you might want to think of as tau 1, 2. And there's an equivalent kind of stress on the backside here as well, and on the underside there. Might be a little easier to envision if you're kind of looking at the 1, 2 plane. So here's like our fibers that are running through. Kind of exaggerating them here a bit. Here's our 1, 2 plane. It's a little easier to see the shear if we draw it in this general direction. So positive 1 face, positive 2 direction, positive 2 face, positive 1 direction, negative 1 face, negative 2 direction, negative 2 face, negative 1 direction. All right, this would be like your applied sigma 6, which is tau 1, 2. This is like a pure shear mode on your composite. What happens is these guys tend to fail in shear right at the interface between the fiber and the matrix. So here, high shear stresses between fibers and matrix at the interface. Okay, so what I mean by that is it's like high amounts of shear like right at this interface here, okay, between this fiber and this matrix. These fibers basically want to like slide out of the matrix more or less. So we're going to end up being like dominated by shear properties of the matrix, because typically the shear stress of the matrix is going to be lower than the shear stress of the fiber. And so what you're going to have is this kind of like shear failure right at the interface between the fiber and the matrix. Okay, so failure will occur in matrix at interface, and it will be a shear failure. All right, so what that's going to look like. Yikes town. All right, I'll try my best. Okay. Okay, so here we are. And again, we've applied like this sort of shear here on this guy. Right. And we're failing right at the interface between what would be a fiber and the matrix right next to it. So usually the failure occurs like you'll see a clean fiber surface break. And then right here, this is the matrix that like was attached to that fiber right there. All right. So maybe we got a couple more fibers in here. Maybe there's another one here. Okay, something like that. And it's because there's just so much like shear that's occurring right there between the matrix and the fiber. We have kind of a similar idea here going on with like stress concentration, but it's not exactly stress concentration. we're trying to like shear across some plane that has a bunch of fibers in it. The fibers are actually causing additional shear concentration, just like you have stress concentration in like the 2 and the 3 direction. You actually end up with like a shear concentration between the matrix and the fibers. It's a little bit difficult to draw, so it's not really easy to draw, but we'll just say here there's a shear concentration from fibers. It's a little bit like the stress concentration that you have kind of in the 2-3 direction when you load that way. And so our failure in 6, you sort of put that all together, and you have here this F6. Remember, this is failure in the 6 direction, or F12. Typically, it's just denoted as F6. Is going to be the failure strength of the matrix in shear, FMS, divided by a shear stress concentration factor, K tau. So F6 shear failure strength of composite FMS. This is the failure strength of the matrix in shear. So the matrix shear strength. And finally, K tau is shear stress concentration factor. And this has a mathematical derivation as well, based on the cubic packing theory, which is the following. Going to look very similar to what you saw for sort of the stress concentration factor for square packing. Here in the numerator, 1 minus volume fraction times 1 minus the shear property of the matrix divided by shear modulus of the fiber 1, 2. This all on this wonky denominator that comes from cubic packing theory. 4VF on pi. Multiplied by this 1 minus GM on GF1, 2. All right. Just for clarity's sake, this is not contained in the square root. I've seen that mistake from students in the past. This square root is separate from that second quantity. Okay, so please be aware of that. These are separate sort of quantities. I just saw you furiously erasing. Did you write it that way? Okay. As soon as I said that, Hannah started furiously erasing her paper. I was like, oh, it's a good thing I said that. All right, so there's your shear stress concentration factor, K tau. Okay. We have questions. Or are people still commenting with, I'm seeing that's fire. Wait, that's the same actress? Yeah, Mila Jovovich. Orange-haired girl in, you know, that movie with the Stones. Okay. So that sort of concludes our micromechanical strength notes. All right, we've talked about what's the strength in the one direction in tension, what's the strength in one direction in compression, 2-direction tension, 2-direction compression, and what's the strength in the 6th direction. All right, which is like the shear direction. That's all well and good. But when we're talking about composites, we don't just load them in the 1, in the 2, and the 6 directions alone. Okay? We're going to have more than just loading in 1, loading in 2, loading in 6. So we want to talk not about the strength in just the one direction or the strength in the two direction, but we want to talk about strength in some arbitrary direction. Obaid asks, what's FMC? This is FMS is the failure strength of the matrix in shear. FMC is the failure strength of the matrix in compression for Obaid. Good. This comes up for F2C. Okay, that's where that's coming from, David's asking. Okay, so, right, we've got F1T, F1C, F2T, F2C, and F6. Great, fantastic. But we know that composites are loaded in complicated ways. So we have F1T, F2T, F1C, F2C, F6. That's nice. But what about strength in arbitrary X, Y coordinate system? Question mark. So if I've got some composite that looks like this, okay, unidirectional composite, I got all my fibers going in this way, turned it on its side. All right. What if I load this guy in this direction with some stress sigma x, so that I have some coordinate system that's here, that's like the x, y coordinate system. Okay. So here, what then is fx, or more carefully, what we are going to prove or show in this class is what sigma x would cause failure. Okay, and this is what we'll talk about next time. All right, get you out of here about 10 minutes early. Little teaser for next time. So that's it for today. Thank you for coming and putting up with my nonsense about fifth element. Everybody likes nonsense, keeps you awake, sort of.